Okay, we're talking now about radioactive materials. All right, we've got a small quantity of radioactive material taken from a nuclear reactor, and we want to prove that this thing is releasing gamma rays. Now, this is where you've got a bit of freedom, I think, okay, because there's actually 3 correct answers to this, and I've tried very briefly to describe these 3, all right? There are 3 methods I would use, okay? In each of them, what you're going to have to do is mention that you'd use a Geiger-Müller counter. And that Geiger-Müller counter, if you remember, is the thing that we use to detect radiation. Okay, so you've obviously got a material. Okay, I need a detector to see that I've got some kind of radiation coming out there. So please mention that in any of these guys, and it's you can call it a GM tube, GM counter, GM detector. The first method I would use is just absorption, right? And I'll try and draw it up at the top so you've got an idea, okay? Remember we had this idea of paper, aluminium, and then lead, okay? We have paper, aluminium, and then lead, PB, lead, okay? You have your counter here, okay, and you have your radiation here. Now, this is gamma. What that's going to do is it's going to pass probably a bit through all of them, all right? But the test that you would do is we'll say start with paper, check the reading on the counter. It would have a high reading. Add some aluminium, it would have a lower reading, and then add this one, it would have a lower reading then. Okay, so that suggests it's gamma because it's penetrating through paper and aluminium. So you can use paper, aluminium, and lead. Using lead, the gamma would be absorbed. Another method is using an electric field. Remember, we had positive and negative. All right. Remember, alpha will be is positive, and so it will be deflected by our positive plates. Our beta, will be deflected by our negative, whereas gamma will pass straight through. So this is your gamma coming right through there. Okay, this is our beta, alpha. All right. So again, you could use that. You would show that you would apply an electric field. However, your radiation wouldn't be deflected. You would just have your detector somewhere here, waiting in line, and nothing would happen to it. Similarly, you could do a magnetic field. Ooh, good application of our left-hand rule. Okay, field into the page. My alpha would be deflected up. Okay, my beta would be deflected down, and then my gamma would go right through. Okay, so in both the E field and we call it a B field, magnetic field, the gamma will be undeflected. Alright, so that's 3 of those potential ones that you've got there. We then have a decay equation to do. We've seen this before, people, haven't we? We've seen this a lot of times. Pu, plutonium, mass number or nucleon number of 239, okay, atomic number or proton number of 94. Alpha is 4,2 helium, so we'll just stick that right there on the right hand side. Generally the convention is we have it on the right hand side, doesn't have to be. Okay, then we just need to make sure those numbers balance. 239 minus 4 is equal to 235. 94 minus 2 is equal to 92. That is uranium. You are told that it's uranium as well, so you shouldn't need to look it up. All you have to do is write it down. Okay, again, I've said this a few times now. I think I've seen this about 4 or 5 times. There has been one slightly different equation, okay, which was using, I think, maybe beta decay, or simply we started with a different isotope. You're doing the same thing every time. Here's a nice one. Okay, here's a good question which I think is worth having a look at properly. Electricity produced by a nuclear power station is transferred to a nearby town using overhead power cables. We're learning right now about transformers, all right? We know that that thing is stepped up, okay, to reduce power losses. Now, the resistance of this thing is given by this equation. This is an equation you've not learnt. However, it is one that you should be slightly aware of because we have seen this behavior in our class, all right? One length, right, L, of an overhead power cable has a resistance of 7 ohms. Then we're being asked to predict the resistance of a cable that has half the diameter but same length. So in other words, this is not changing, okay, and this is going down, all right? So your check is that if this is staying the same, this is going down, this resistance must be going up, all right? that is something that you need to be aware of. Your answer should not be less than 7. What should it be exactly? Well, here's a bit of maths. I know, horrible. We've got to use some math skills in our physics paper, but it's completely fine. The area, there's a few ways of writing this. Area is pi r squared. All right. Okay. Well, another way of writing that is area is pi d squared over 4. It doesn't really matter which way you do this. Okay. If we have the diameter, yeah, let's think about it. If d goes to half d, then d squared goes to d over 2 squared, yeah, which is d squared over 4. And what that means is we are quartering the area. So the area has gone down by a factor of 4, which means my resistance must multiply by a factor of 4. Okay, I've tried to express it here. R is inversely proportional to area. So area goes down by a factor of 4. R goes up by a factor of 4. 4 times 7, 28 ohms. Let's do our check. Well, we said it should get bigger. Definitely bigger. Okay. We've now got our generator. Okay. All we're being asked to do here is sketch the voltage output for a generator, remembering that a voltage output from a generator is AC. In other words, it's that sine curve. Okay, so try and draw an approximate sine curve. I've tried to do this way by what I did was I decided the wavelength of my sine curve. I put little dots here and I just drew a curve. I tried a curve here from A to B and I took a rest. Curve A to B, sort of B to C, C to D, D to E, E to F. All right, that's the way I did it. As long as it's approximate, that's okay. It doesn't have to be perfect. It should not be straight lines or triangles or squares or anything. The thing that you have to make sure is that your amplitude should always be consistent. So I've gone for 2 boxes here, 2 boxes, 2 boxes. Okay, you could go right up to the top as well. It's up to you. We are then asked how to increase the size of our induced voltage. Okay, well, there's a number of ways of doing this. The one that I would suggest is the best, rotate it faster. Okay, and rotating it faster will cut more field lines. It will therefore generate a higher, induce a higher EMF. You could, however, also use just a stronger magnet, okay, or add some more coils. All right, each of those coils gets a small EMF. If I add another coil, I get more EMF in total. Last little bit from here. Okay, I like the way they link this together. We've now got a generator which is emitting sound waves. Okay, it's not what we want. This is not efficient. Okay, the sound waves have got a speed of 340 meters per second in air. Okay, and we've got a frequency. Notice those numbers are very, very similar. All right, okay, that's fine. We want to know the wavelength. Well, our equation linking speed, wavelength, and frequency is V equal to F lambda. Okay. Again, you need your own way of working this out, of remembering these. Okay. Lambda is simply the ratio of V to F. We've got 340 divided by 490, so in other words, 34 divided by 49. That gives me 0.694 meters. In other words, you're talking 70 centimeters, all right? So these sound wavelengths can be of a number that you might be able to link, all right? So basically, if I'm looking at that distance here, that is the wavelength of my sound wave. Sometimes very tempting to think these wavelengths are very, very small or very, very big. It really depends on the frequency of the sound that you're dealing with. Okay. Last bit, this is our diagram, and again, this should be something it's come up a few times. Okay. These were our compressions. All right. Compressions, literally where those things are close together. Now, the question, first they ask you to label. I've gone a bit crazy. I've labeled 3. I don't think you get any trouble for that. The most obvious one's in the middle there. All right. But these guys on the side, they would be fine as well. Okay, the generator turns faster and the frequency of the sound increases. And what I've just done there is I've labeled F goes up. Okay, I'm trying to reduce the cognitive load on myself. All right, by writing things down so that I can just have them there to look at. Well, we've then been asked, how does the distance between the compressions change? That's quite a nice question. Okay, you don't have to explain why, but so really you've got 3 choices. Increases, decreases, stays the same. In this case, the answer is decreases. Okay, so if you're going to guess, fine, guess an answer. However, I want to think about why that is. We've got this equation V equal to f lambda. And this always holds for our sound waves. All right, we're being told that we have to work under the assumption, that v is constant. Okay, sound waves all sound waves in air travel with the same speed, 340, 330 meters per second. All right, you're being told that f goes up. Well, in order to maintain that, then lambda must also go down. This holds for sound waves, and it holds for light waves as well. It holds for water waves. Well, the result of that then is that lambda's going down. How does that relate to this distance? Well, lambda is the distance between the compressions. So what you'll find is you'll have more compressions over this distance because we're producing more waves every second as a result of increasing our frequency.